Hello everyone. In this video, I will explain the fundamentals of timing verification. As an example, I will show how to verify the timing of a multiplier module, and finally, I will show how agentic AI tools can dramatically speed up the verification process. So to start, let's go over how a Verilog module is made. When making a Verilog module, there's always two steps. The first is getting the Verilog module to be behaviorally correct. A Verilog module is considered behaviorally correct when the source file always produces the correct output. The second is getting the Verilog module to be timing aware. A Verilog module is considered timing aware when its implementation can run at high clock frequencies. So what makes a design fail timing? When a Verilog module does not meet timing, the failure point is almost always going to be one of these two reasons. The first is when combinational logic is too deep. A combinational logic block is considered too deep when its delay is too large to complete within one clock cycle. The second is when a signal has high fanout. High fanout is when the signal is being used to drive too many inputs. So how do we fix deep combinational logic? When timing fails because the combinational logic is too deep, the fix is to pipeline the design by dividing the logic into smaller stages and inserting registers between them. The price we pay is that each register adds an extra clock cycle. A classic example of this fix is shown in the example below, where an arithmetic module computes y equals a times b plus c minus 7. The non-pipelined version tries to do it in a single cycle, making it risky in terms of timing. The pipelined version divides the computation across 3 stages, making it more robust in terms of timing. So how do we fix high fanout? When timing fails because of high fanout, the fix is to duplicate the driver of the high fanout signal and have each copy drive half. You can duplicate as many times as needed until the fanout problem goes away. The price we pay is that more resources need to be used. To get the timing report of a module, we must make a wrapper instantiating the module and implement it. A wrapper's purpose is to reduce the top-level module's I/O while ensuring that the module under test is not optimized away during implementation. A wrapper is made by generating the module's inputs with internal registers, registering its outputs, and combining those registered outputs into one or a few top-level signals. The figure below shows the basic structure of a timing wrapper. After implementing the wrapper, you can get the timing report. The timing report lets you know which part of the design failed. The timing report will reveal if the failure was due to dense combinational logic or fanout problems. The steps to locate the timing report are shown below. Behavioral and timing verification provide the feedback needed to iteratively improve a source file. After each revision, the source file is behaviorally verified, wrapped, implemented, and analyzed through a timing report. This cycle repeats until the design remains functionally correct and achieves timing closure. Agentic AI can already automate this entire flow, allowing source files to be revised, re-verified, and re-implemented with far less manual effort. Alright, so now let's verify the timing of the multiplier from the last video. Alright, so this is the Codex folder from the last video. In the multiplier folder, there is a folder containing the behavioral verification, and there is a folder containing the timing verification. The behavioral verification files were made in the last video, so those files will not be explained again in this video. In the timing folder, we already have a pre-made wrapper for the multiplier. We must bring that wrapper into Vivado. As you can see, the wrapper uses the robust methodology discussed previously. the inputs of the source file are all registered internally, and the wrapper logic ensures that those registered inputs keep changing internally to prevent the synthesizer from optimizing the module away. The outputs are registered, and those registered outputs are combined into the keep alive signal to prevent the top-level I/O from getting too large. Once we have the wrapper in Vivado, we must add the constraint file. This here shows the constraint file. Then we generate the bitstream. From the generated bitstream, we can already see that it passed timing. Regardless, we still want to export the timing report into the timing folder of the multiplier. After we export the report, we can access the detailed timing report in the text file that Vivado generated at the chosen directory. Now let's explain how to use Codex to automate timing verification. To demonstrate the process, we will use the divider module from the last video. As you can see, the divider module currently only has the behavioral verification files. To obtain the wrapper for the divider, we do not need to write the wrapper ourselves. If anything, writing the wrapper would mean a mundane waste of time, since the methodology used to make the wrapper is always going to stay the same, regardless of the module being verified. Fortunately, Codex and other modern AI tools can reliably automate this process. To open Codex, we must cd into the Codex folder. Then we type in Codex. I will skip updates. Then, to get Codex warmed up, we ask it if it understands the project files. After it responds, we can then prompt it to make the timing verification files for the divider. A good prompt will explain the robust wrapper design and explain how the multiplier and extra example folders provide good examples of the methodology. A good prompt will also say to make a timing folder for the timing verification files. After sending Codex the prompt, wait for it to finish working. This can take a few minutes. Then once it is done, we can access the wrapper that Codex made for the divider. We can copy it into Vivado, reuse the same constraint file from the multiplier, and implement it. From the generated bitstream, we can already see that it passed timing. Regardless, we still want to export the timing report into the timing folder of the divider. After we export the report, we can access the detailed timing report in the text file that Vivado generated at the chosen directory. If the timing report had failed, the next step would have been to have asked Codex to diagnose the cause of the timing failure. We would then ask Codex to modify the source file by targeting the timing problem. The problem would usually be either deep logic or high fanout. After that, we would rerun behavioral verification, update the wrapper, and generate a new timing report. By repeating this process, the design would have eventually become both functionally correct and timing aware. Alright, so if you have made it to the end of the video, you should now feel confident in your ability to verify the timing of any custom Verilog module. You should also feel confident in your ability to use Codex to automate the process with great efficiency. Alright, that's all for this video. Thanks for watching, and I look forward to seeing you in the next one.